Let me introduce our next speaker, Dr. John Seaman. John is a senior research professor and associate director for research with the University of Georgia's Savannah River Ecology Lab. He received his bachelor's and master's degree in soil chemistry from Texas A&M, and also a PhD in environmental soil science from UGA, University of Georgia. Working in collaboration with various site contractors, he has over 20 years of experience in addressing heavy metal and radionuclide contamination at DOE's Savannah River site, including the use of cementitious materials for the long-term disposal of radioactive waste. He has over 80 peer-reviewed publications and served on a number of review panels for DOE, USDA, EPA, and the National Science Foundation. Much of his work has focused on the development of in-situ soil and groundwater remediation methods, more specifically on the use of reactive soil amendments. Welcome, John.
Thank you. Oh, there it is. So if anybody has any questions, feel free to just ask questions as we go through. I want to start off by acknowledging my collaborators, Stephen Simner, Hyun-Chi Chang, who is now he's a postdoc, he's now at Hoganus, North America, and then Fanny Cotelat, who is a current postdoc working in my lab. So one of the things they like me to always emphasize when going to a new group is that even though I'm a University of Georgia employee at the Savannah River Ecology Lab, that we actually do research besides studying alligators and snakes. And that's the general idea that most people have about the Ecology Lab. The actual research that I'm going to talk about today was funded by Savannah River Remediation. Next slide. Technetium. This is good to follow Steve because he's already given you a lot of the background. Technetium under oxidant conditions is in the +7 redox state. It forms the pertechnetate monovalent oxyanion. It's very, it tends not to absorb in soils. The one exception of that is the highly weathered soils of the southeast. This is the only soil part that I'll tell you about, is that our Vado zones and our soils in the southeast will actually absorb a considerable amount of pertechnetate, also iodide and iodate as well, because of the higher iron oxide content and the very low cation exchange capacity of the materials. But because the reduced form is much less soluble, most remediation efforts or immobilization efforts focus on trying to put it into the reduced form, usually a Tech oxide. But the problem is that Tech 4 can be readily oxidized back to Tech 7 under even moderate O2 exposures. So one of the things that's good about cement and grout, though, is that what we're doing is we're relying on both the physical and the chemical integrity of the material to keep it in place. And we'll see why, well, the best example of why we need to look at these materials more in intact form is simply, if you see some of Steve's data, is you do this under an oxic environment and you get a much, much lower KD or a much higher solubility than you see when you do it under the environment that might be more in line of what is actually the pore solution. This is a solubility diagram of reduced technetium, and we use this to try to predict what the solubility will be in these various materials. Next slide. A couple things I forgot to say is that technetium is a very low energy beta emitter, and it has a 200,000 year plus half-life. And so that drives some of the problems with the risk. This is third quarter of 1 year analysis of the tank 50 composition that goes into the making of salt waste. And what you see here is we have about 20,000 picocuries per mil of Tech 99, but we have over 1 million picocuries per mil of cesium-137 in the material. So if you look at simply the activity of the material, about 99% of it at the beginning is all cesium-137. But you project out to 1,000 years, even you start getting there after 100 years, is that all of that then for the next few 100,000 years, the activity is all associated with the Tech-99. And then after you go out even farther, because of its higher half-life, is iodine-129 can become important. But we have a much higher amount of Tech-99 in the sample. So one of the consequences of this fact that you have a fairly high-tech concentration, but you also have such a long half-life, is the fact that the actual mass of Tech-99 in the samples is quite high. So at this level, we're looking at 1 to 2 ppm of Tech-99 in these solutions, where these others that can contribute to the activity are actually fairly low. Next slide. So the experiments, I know it's really hard to see this. So the experiments I'm going to talk about, we looked at saltstone simulants that were spiked with stable iodine-127, rhenium. Rhenium is in the same column in the periodic table. So it also forms a +7 perenate monovalent oxyanion under oxic conditions, and so it's very often used as an analog for technetium. Then we also spiked them with Tech-99. We looked at multiple blast furnace slag sources because that is where the inherent reduction capacity comes from that we're relying on to immobilize the technetium. We're curing, actually we'll show some data on some samples that were only cured 3 months, but we're curing much longer times than a lot of times people do in these kinds of experiments. And the other thing that we're doing that they don't do quite often in looking at some of these is we're trying to match the temperature regime and the humidity regime within the vaults that Steve talked about. So in addition to the actually simulated cores, we also have 3 samples of the SU2A samples that Steve was talking about earlier. Now we did the EPA 1315 mass transfer test that was developed at Vanderbilt University by Dr. Kassen's group, which is very similar to the ANS 16.1. And then finally, I want to talk about this dynamic leaching procedure method that we're developing here at the SRS. Next slide. So this is actually the simulant chemistry, and then here it's a 0.6 to 1 ratio of wet to solid material, and so this is what it looks like when you first mix this material up. If you look at the chemistry though, it is very high in nitrate, high in nitrate, high in nitrite. It's got quite a bit of carbonate in it, also quite a bit of sulfate and quite a bit of aluminum. The important part about this, though, is that these, especially the sulfate and aluminum, are all constituents that can have a significant impact on how cements cure and their final properties. And we also use these often as actual additives for developing various properties in cement materials. Next slide. So, as Steve was saying, to try to mimic the actual vault conditions, we use these very expensive ovens that are able to both keep a very, very high humidity and a high temperature at the same time. And we do, we try to mimic the temperature of the grout at the extreme actual curing temperatures that we see in the vault and the very high humidity. Next slide. So this is EPA 1315 that we're going to talk about first, and we did it 2 different ways. You can do it as a 1D sample or as a 3D sample, and what we're talking about is this is a simulant that's still in the curing core, and we've simply sectioned it off at 2 inches above the bottom, and then we place it in the reaction chamber, only exposing the top of the sample and the fresh cut. And if you look at all of the samples that Steve was showing, is they have more of this kind of brown gray color, but when you get inside the actual inner material, and it's very fresh. What you get is this more dark green color indicative of a reduced inner sample. And so because we're exposing about 20 cubic centimeters, the EPA test actually says what the solid to solution to exposed surface ratio has to be, and it's a 9-to-1. And so the sample is down in here, and it's actually in 180 mils of water surrounding it. Now, what's unique about what we did is we also did this test under 3 different atmospheres. We did it under air, ambient air, ultra-high purity nitrogen, and a combination of nitrogen-hydrogen mixture that you often use in coil chambers to keep the redox conditions low and make sure you have no oxygen. And what we did is we took the water, and it's this artificial groundwater solution, and we equilibrated it with those solutions before we put it into the sample, and then we also put all of these samples inside the chambers to make sure that the atmosphere around the samples was consistent with the water that it's being exposed to. The next step that we did, and this included both spike cores and SU2A cores, is we did the 3 tests in which you measure all of the surface area associated with the intact part or monolith, and again you put it in solution for various amounts of time. When we start looking at some of the results, though, it'll be clear why we only did this in air for this second test. Next slide. So if you run the EPA 1315, what you do is you take 9 samples over time, and down here is from the actual method itself is a diagram. What you do is you take the monolith, you put it in the solution for a set amount of time, then after you put it in a new solution for a set amount of time, and you do this over and over again, and you take those solutions, and that is what you analyze then at the end of the experiment. And so you take 9 samples over 63 days. Next slide. So this is just a little bit of the data for Tech 99 spike simulants. This is the type of data you generate up here. This is over time. I know it's very hard to see in the back. So going over the 63 days, but this is Tech 99 in solution under the 2 extreme environments. So under the atmospheric conditions, oxic samples, and then under what I would consider reducing samples because of the high hydrogen level in the solution. And what you find is that, sure, there's a little bit of differences between the 2 in the various samples, but when you start looking at the actual cumulative amount, it was completely insensitive to atmosphere. And so this is in direct, this is directly opposite of what you see when you grind material up. And so this just suggests that even though we're trying to expose it to the atmosphere that it might be exposed to, that inside the material, it's still controlling its own chemistry. Next slide. So what we try to do with this data over time is calculate an effective diffusivity. And the thing that's important to recognize in that is that we have to be very, very careful about how we interpret the effective diffusivity, because within that, it's not necessarily a real diffusion factor. There can be lots of mechanisms controlling the release, but this is just a way to actually analyze the data and compare different sets of data. And what you do is you use the effective diffusivity to calculate a leaching index, and that is the negative log of the effective diffusivity. And what that means is that if it's leaching slower, coming out, it's more immobilized within the material, then that effective diffusivity goes up. If it's actually leaching faster, then the effective diffusivity goes down. Next slide. So if you actually plot the material or the 63-day data on a log plot, and this is data for rhenium and data for iodine-127, what you see is you should get this decreasing flux over time, and on a log plot, it should have a slope of -0.5. And what that says is that you can kind of use this way to interpret the data. When you start seeing significant differences like we see out here at iodine 127 at the very long times, what that is actually a reflection of is that more than 20% or so of the iodine that was in the sample is already leached out. And so these data are a little bit invalid in trying to use this approach for getting a leaching index that you can compare with other data sets. The other thing is that these were the 3 different treatments, and what you see is that for both rhenium and iodine 127, you don't see any difference, really. Essentially, all of these lines are on top of each other, and also, if you try to rank them as to which one you think would be more immobilizing, it doesn't seem to follow the pattern that you would ever say. So you don't see that the reducing one is always the slower flux, while the oxidizing one is always the faster flux. It just looks like experimental noise. Next slide. So this is comparing just Tech 99 versus rhenium and nitrate. And this is cumulative extraction, so we have to have a very good idea of what our initial starting point is. But what you see is that both rhenium and nitrate come out of the sample at essentially the same rate in terms of their percentage coming out, while technetium is very low. I put the iodine 127 up here just to say that you see the exact same thing with iodine as well, even though I didn't want to make the graph so cluttered. Next slide. So here are the 3. So essentially this led us, when we went to doing the 3D test, to say that we no longer need to do these under 3 different atmospheres. That the original way that the procedure is written is a good way of evaluating what's actually gone on inside the intact materials. So this is Tech 99 coming out of the 3 SCU samples that we evaluated over the 63 days. And that's actually in terms of hours. But what you find is that there's a little bit of experimental difference on individuals. But when you go back and you plot cumulative on all 3 samples, is that they're right on line with each other. And there was very little variability in terms of tech leaching out. Next slide. Cesium's a different case. So what we found is that we had one sample that cesium-137 was coming out of much faster. And that's evident down here. You've got 2 that are pretty close, and then you've got 1 that's kind of an outlier. And does anybody have an idea of why that is? So it kind of confused me until I went back and measured the cesium-137 levels in these samples, and they were really different. We had one sample that had almost twice the cesium-137 sample of the other 2 samples. So even though we think that things are going in and that they're always fairly homogeneous, you can have differences. And it seems to be differences with respect to one contaminant that you don't see with respect to the other, because the technetium levels, you did see big difference in those in these different materials. So that's a very unique system, or that's a very unique finding. But the thing that's important about this is if you don't know what the initial inventory is within the sample, then that can really skew all of your calculations in trying to get a leachability index. So you have to have a good handle on what's in the material. And another example of that is iodine 127. I was getting a huge amount of iodine 127 coming out of the sample, more than I put in. This is actually a different mechanism than what Steve was talking about. But the reason was because there was a considerable amount of iodine in the raw materials, in the dry materials, and the fly ash had some iodine in it. And I had to add that to the base number before I got the data to make any sense. Next slide. So the other thing that we saw is after they switched providers of blast furnace slag this last year, and we went from the wholesome blast furnace slag to the Lehigh slag, and what you see is that the spike samples give us, using the Lehigh new slag, give us a much higher leachability index, or much less coming out compared to those associated with the earlier wholesome source. And if you look at the reduction capacity, we went back there then and measured the reduction capacity of the different materials, and we found that the new source has a much, much higher reduction capacity than the old source did. And looking at its composition based on XRF results, it also had a much higher iron and a much higher sulfate, or not sulfate, sulfur concentration, which are thought to be the two reducing agents that are in blast furnace slag. Next slide. So this is just to summarize the leachability indices that for all of these studies. And what we found is this represents, the ranges up here represent more than 6 different measurements. I'm not going to call them reps because all of these include all of the different atmospheres. It's all bulked together. And what we find is close to 10 for tech, around 7, 7.5 for rhenium, nitrate about 7, 7.5, and iodine about 7.5 as well. If we go down to the new material, as we were talking about earlier, we get quite a bit higher leachability index with the new material. It has a more higher reductive capacity than we do with the old. And then also when we go back and look at the 3 STU cores that we're using, the old material, it actually has an intermediate value between, even though it was the older Holston blast furnace source, what we think is that this has been cured 20 plus months before it was ever drilled out. And so that even suggests that there may be some kind of curing duration effect that we see in this data. The other thing that's important is that a lot of these values are very consistent with values that have been observed in cast stone as well for similar tests. Next slide. So we were talking about measuring saturated conductivity, and so we did a lot of these measurements on some simulated materials. And what we found is that even if it was around 1 times 10 to the negative 9, we could get continuous leaching through the material at relatively low pressures just by keeping the material on a flex wall permeameter. And so that's an example of right in there is a piece of core that we're putting the flexible membrane on, and then it gets put into the chamber for measurement. And what you're doing is we're forcing artificial groundwater through under pressure, and then we're collecting that at the effluent and measuring the how that effluent changes over time. The one thing that's important to note is over here on this side is a large permeameter instrument to do these experiments, or manifold, right? Is the right word I'm trying to think of. And we'll see why that's important and how we change that as we worked on the system. Next slide. So this is a better diagram of the entire system, and what you have here is some of the tubing actually disappeared in this version. I don't know what happened. What you have here is you have your confining pressure on your sample in the chamber. You're applying then a driving pressure for leaching, and then you're collecting the sample at the effluent here. And so that is an actual picture of the system as it exists. I'm sure I didn't miss something. The one thing over here is this is called a separation bladder or attenuation bladder, and what it allows you to do is keep your inlet solution completely isolated from the atmosphere before it goes into the sample. So you can control what the dissolved gas levels with the sample going in are. Next slide. So here, that was the first generation, and with one manifold, which is a very expensive piece of equipment, we could measure one sample at a time. And so what we went back and made a much simpler system. And essentially all it is you just need 2 valves per sample. We've only set up 2 samples here, but we have a valve for your confining pressure, a valve down here for your actual leaching pressure, and then we only have one pressure transducer because we have toggles that allow us to go through and measure what the pressure is on any of these given valves. So we can do 3 at a time for very, very low cost. The other thing is we can also use this to just measure hydraulic conductivity, especially if we're going to measure it on very low samples, when we add what's called a thermometer to measure the change in flow over time. Next slide. So today we did a bunch of samples that were spiked with rhenium. We did one spike sample with technetium, and we also now are doing some SEU samples as well. And consistent with what we saw before is that rhenium came out of the sample very, very fast compared to technetium. The other thing that's important to note, and Steve talked about this a little bit, I have this on a pore volume basis. That's a little bit arbitrary. It was just a way to compare different samples. And we're working on different ways to try to get a handle on this. And the one thing that we've tested early on is we can actually do a tritium tracer experiment through this material and get a better idea of what the actual conductive volume is, because it's likely much, much less than what the porosity measurements tell you might be. Next slide. So here's some of that data. This is the effluent pH of 3 different samples and out to 6 pore volumes. And this is, you see, for the 2 SEU samples, we see them starting out at about 12.5 and going down very, very quickly. For the tech spike samples, we have it going down, and we're missing data up here. Here's the problem. We started out trying to use flow-through cells, and the actual flow rates were so low that they were completely useless. The other thing is, if you're collecting a sample and you're collecting 1 or 2 mils a day and it has to sit on the counter, the pH of those samples went down by about 1 to 2 units just before you could ever measure it. And so there's a lot of potential error in these measurements in these samples, especially with respect to pH. Next slide. Hydraulic conductivity. This is another one of the problems. The good thing is that what we found is that one of the samples had an initially high hydraulic conductivity, one of the SEU samples, but quite soon it went down very quickly. The same for SEU-A. It started out at about 1 times 10 to the negative 9 and went down from there. While the degassed spike sample seemed to maintain its hydraulic conductivity over time. So I didn't touch on this, but what you have when you're doing this system is you have a inlet pressure, you have a flow rate at the outlet, you have a known dimensions of your sample, and so you can always calculate what the hydraulic conductivity is on this material as you go with this experiment. Next. So this is cesium-137. What you have here for one of the samples is that we have very little data, but it seems to be like it's going down, and it's following the trend that we have for the second sample, the other SEU samples. We only have the 2 SEU samples because there wasn't cesium in any of the laboratory spike samples. But we start to see strange things happening. We see the cesium-137 level go down for a while, and then all of a sudden it comes back up. And this coincides with when hydraulic conductivity goes down, the flow rate goes down, and the residence time goes up. So this seems to be clear evidence for some kind of residence time effect going on. But we also have to realize that there are 2 very different cesium levels to begin with in these 2 different samples as well. So that can have an influence as well. Next slide. If we look at the technetium, one thing that's important to note is that the levels are much lower than what the inlet levels were with the solutions. But we have the SEU-A and this SEU-B samples. We still have fairly high technetium levels coming out in these initial pore volumes. And what you can say, though, is that at those initial high pHs, these are fairly consistent with what the technetium oxide solubilities would be, even though they're a bit high. This other one, the simulation, it was very low until way out here after we've gone through several pore volumes, and then all of a sudden it started to come up. And so this, while it coincides actually with a decrease in the hydraulic conductivity of that sample, so it could be a residence time effect as well. But it also could be something to do with changes in the phases that are controlling solubility and controlling the way water moves through the system. Next slide. So even though we're seeing those kinds of results, what we can say is when we look at cumulative amount of these things coming through is that we still have cesium-137 coming out of the sample at least twice the rate of technetium for all of these different samples and all these different treatments on a cumulative basis. Next slide. Also consistent with the intact leaching experiments, we see that nitrate is coming out of the sample at a much, much, much faster rate than technetium or cesium. Next slide. So I want to briefly summarize some of the conclusions and then give you a little bit of background about what the next steps are going to be. So what we found is that rhenium iodine 127 and nitrate leach at similar rates, and I use the term non-reactive. That's not actually the right term, but they have a much lower leachability index than Tech 99. Tech 99 leaches at a slower rate. The Tech 99 results are very consistent with what has been reported for the Hanford cast stone. The extraction atmosphere didn't impact rhenium Tech or iodine 127 leaching at all. And there are two different ways to try to rationalize this. The first way is that you could think of is that rhenium is so hard to reduce compared to technetium, and that maybe we never even reduce rhenium. And so it doesn't really matter. It just comes out fast regardless. But then compared to Tech, it seems like we are able to reduce technetium. And so we get completely different responses simply on, based on whether it's reduced or not. The other possibility is it's actually hard to get some very reliable data on rhenium, but rhenium solubility can be orders of magnitude potentially higher than technetium in these oxide phases. And we also have ongoing tests with iodine 129 in the SCU grounds. Next slide, please. For the SCU cores, we got similar Tech leachability observed for the SCU cores and the similar materials. We did seem to have some kind of indication that the blast furnace slag source and curing time were important. One of the things that's interesting to note is that before this, you look at a lot of the literature and a lot of the different tests, that it didn't really seem to matter. Every lab and every experiment that tried to measure the reductive capacity of these different blast furnaces almost always presented a number that was very similar. It didn't seem to vary that much between different materials. But that was very different from our newer source. And the cesium-137 actually came out slower than I would have predicted because it's generally thought that it's held mainly as an exchangeable ion. And I would have thought at the ionic strengths that we're looking at that it wouldn't be very competitive at these low levels, but it actually was. Next slide. So the DLM tests, we have variable residence times, which makes it very hard to actually interpret the results. The KDs for these simulants were very similar to what we expected for the SCU cores or for other reports of what the solubility should be or what the KSAT should be. The rates of leaching generally followed what we would have expected. We have nitrate coming out of there much, much faster than cesium-137, which is coming out faster than Tech 99. And though we have some increases that are hard to interpret, it's generally consistent with the Tech oxide form that we talked about earlier. So how do we fix some of these? Next slide. How do we fix some of these problems? Yeah, next slide. So what we're in the process of doing is modifying the DLM system. And we have the new system will have the ability to have a constant inlet flow rate that is adjustable while we're measuring pressure. So we'll still have all of the data that we need to look at what the conductivities or the physical changes of the material are, what the materials are going through, but we can more reliably control residence times. And so what we're targeting is a residence or a flow rate of about 1 milliliter per day. And what we think is we can actually do twice that and look and see if we can see a residence time effect in these types of experiments. We also have the ability with the new system to automate the control of the confining pressure. And so what you really want to do, and what's very difficult with these kind of samples that are changing over time, is you want to adjust both of those pressures together, and so that you're always about 4 psi higher on the confining pressure than you are on the inlet pressure to make sure that the column doesn't blow up because of the inlet pressure. We also found some very low volume flow through electrodes, 50 microliters. So if we're up around 1 mil, we can see significant turnover in a given day, and we don't have this problem of the samples sitting around a long time. Then the other final solution is there's actually a way to control the back pressure using essentially a piston system that allows the effluent to build up, pushing out a piston at a set pressure, so that you don't have 20 psi on the inlet and 0 psi on the outlet, which can cause problems because the sample can degas. And that can cause a problem with trying to measure anything with a flow-through electrode. And so that solves the problem of that. And it minimizes any kind of exposure of the sample to gases or loss of gases during testing. Next slide. So for FY17, we're going to go back and do more EPA 13 and DLM tests with the 129 spike saltstone this time, because we don't have a lot of iodine 129 samples or data. We're looking at these blast furnace slag source materials to see, we've got 3 or 4 different samples from Lehigh to see if that is just a one-off sample or if they actually consistently have a much higher reduction capacity than what we had in the past. We're expanding the DLM system. We're going to keep those other 3 samples going, but we're going to have 4 controls that now allow us to look at solubility versus kinetic controls. And then we're going to go back and look at a tritium tracer to try to estimate changes in porosity over time of given tests. Next slide. We're expanding this with the help from SRR. They purchased an XRF unit, and in matching, UGA actually purchased an XRD. So we have the capabilities now to analyze the solid phase material over time. So we'll be doing this along with thermal analysis of the different routes as well. Next. Geochemical modeling. We've started doing some modeling of this, looking at the calcium silicate hydrides that are generated in cementitious material and trying to see what's actually the major phases is controlling the chemistry of the material. We're also looking at what the residual reductive capacity of the material is. We're trying to identify using some of these to see more specifically what the Tech 99 that may be controlling. And then we're looking at changes in the material over time, something like carbonation and things that change the properties of the cement over time or the grout. And then we're also doing calorimetry on these materials because of the chemistry is very, very different from simple Portland cement. And so that can have a big impact on the phases that are actually controlling the chemistry of the material. And we've even done some preliminary models, and it's very hard for us to use Portland cement as the controlling factor and get any of the calcium and the sodium and any of those things to come out as what we would expect. And I believe that's the last one.
Thank you, John. Is there any question? Yes, John.
Hi, John Tokes with Neptune. First, I got to say, as someone who's now living in modeling fantasy land, this really, I used to do lab work, and it's great to do. It's great to see lab work. Makes me want to get back into the real world again. So I got a couple questions. One is, what are the implications of this for, the Saltstone, the SDUs that are out there, Saltstone disposal units, and at that scale and at the scale of times that we're interested in? I'm curious what those are, is question one.
Well, I think one thing you have to realize is that I think that this is what we're trying to do is we're trying to look at the chemistry of what's going on in these intact materials. Not necessarily trying to suggest that advection is a controlling factor in how things actually will come out of the grout, because we are having to put a pretty stressful on the system to get the water to move through. But I think, as Steve was showing, is there are very important considerations on how the tech comes through and how that is modeled in terms of long term. And so what we're seeing is that if a little bit more comes out earlier, because of the higher pH of the systems, then that really changes this peak of how things come out at the very end, and has a very well. We've already talked about how those long-term, what the meaning of some of these long-term simulations are, but it certainly really changes what the long-term simulations are of these materials. Yeah, I'm not sure if that answered your question.
Yeah, it was just one of scaling, but yeah, the idea of advection in the end not probably being the main process that's driving stuff, then that's... so the other question is there some way to use this and perhaps additional experiments to design the grout to behave in a particular way in the long term? Because I've long been a fan of designer grouts that will leak at you want them to emit the radionuclides back into the environment at a slow rate that keeps the doses under control, but doesn't hang on to the stuff forever. So that when the grout eventually fails, which it will, maybe you finally release just the last of the radionuclides, right?
Yeah, I think that's a good goal. One of the problems is that these materials are so homogeneous, and predicting what will happen, putting these different kinds of homogeneous construction grade materials together, and then seeing with a variable tank 50 composition what the long term, how you can try to maybe design the grout a little bit better. And that's certainly the case, especially if you look at what the impact of the blast furnace slag is, and just small changes in the amount of sulfur or the amount of iron in that material will be. One of the things, I wanted to put this up here, this is the same slide that we looked at before, but instead is I put these various weathering states of concrete. And one of the things that we see from our data is it looks like we don't start out here in this state 1, that our data suggests that we start out here at a lower pH and a more, you would consider it more weathered, but I don't think of it as more weathered, but I think of it as just the blast furnace slag produces a concrete that's so much different from the Portland cement. And so we don't even go through some of these higher pH stages of concrete weather. Any other questions?
Yeah, I have one. This is Greg Flax, Savannah River National Lab. John, you were noting a mass loading effect with your cesium leaching data, and I think you were hinting that that there was some competition for sites that was maybe you're in a nonlinear portion of the isotherm. Were you able to see that in your leaching data when it was plotted in a semi-log plot? I think you would have seen changes in slope. I mean, what did you have something there that would back up that hypothesis? And then I guess, and a follow-up question is, how did your mass loadings compare to what you would see in the facility? In other words, is this something we need to be concerned about at the facility scale?
So for the cesium-137, if you plot it on the log plot, it still gave you the exact same kind of flux that you would see over time that would suggest that using those equations is valid in those conditions. But they would be shifted for the different materials. And the second part, all of our spikes, we use the exact same concentration as the tank 50. For rhenium, we use the same molar concentration, and that's a larger mass simply because of the difference in the molecular weights. And so we had twice the mass, it's just twice the molecular weight. But our iodine and our technetium spikes were always very consistent with what we see in the sample. We've never spiked any with cesium-137, we've just used those samples. Yeah. A different part of that, though, is a lot of the experiments that have done to try to speciate tech or these different things in saltstone is that the synchrotron methods, you have to really load a much, much higher amount to be able to use those techniques than what we see in these as well. And so there could be some differences in how those two different systems work.
Any other questions for Dr. Seaman? Okay, if not, thank you again. Let's take about 10 minutes break if you could, and come back by 9:45.